Hi guys, and welcome to this, what I believe will be the final video on plane and descriptive geometry, if there are no more requests in, of course. In this video we're going to have a look at some of the, just two more advanced questions that might possibly come up. These would have been quite a popular question on the old Leaving Cert technical drawing course, but still part of the syllabus, so we'll have a look at them anyway. First one here is just I have the model ready, and then I have coordinates for points. I think it's A, B, C, and then a point P out here at the end of this line. So I'll have the coordinates on my page in a while for that. And the question is, find the true angle that this green line here makes with the plane, so or with the lamina. So it's, you know, very simply worded question, very simple setup as well, with our coordinates of the 3 points and then the coordinates of this final 3 points in the lamina and the final point out here, which is joined back in, and is find the true inclination that that line makes with the plane. Now no real nice simple way out of this one. On SolidWorks, there, I suppose what we're looking for in a sense is that we'd like to find a view where the plane appears as an edge and we can see the true inclination of the line to the plane, but it's not even that simple. We'll just get started here. So I'm going to go through it on SolidWorks and then get back onto the page and get set up and maybe take it in 2 stages. But first of all, there's the elevation of the red plane and the green line right there. So that would be the points A, B, C and point P out there. And here's the plan of the same. Now, what we'll do is, as I was kind of saying there a minute ago, you know, we're going to be looking for a view that shows the plane as an edge view, and we're then going to be looking at what angle or how we can work with the line to find a true inclination it makes to the plane. But to see the true inclination anyway, we will definitely have to see the plane as an edge view. Okay, it's the only way to get close to seeing the true inclination. So in just taking one step along the way towards our solution, we're going to get an edge view of the plane. And just like loads of previous examples, to find the edge view of the plane, we might use our strike line or our horizontal cut there in the elevation. So cut the plane horizontally in elevation, project that on down to plan, and draw your true length line in plan. So if it's horizontal in elevation, it's a true length in plan, and then view along that true length line and set up your x1, y1, which will give us a position to drop in our auxiliary vertical plane or an extra vertical plane for our next view. Project everything from the plan. Now I'm really moving through this quickly, and if you're unsure in any way, you need to go back through my previous videos and see about whatever it is, whether it's getting edge views of planes using our horizontal section cut method, or it's whatever part of this. If you're stuck at these basic steps, go back to some of the previous videos on plane and descriptive geometry that I have uploaded here. So moving along, so projecting all of the points from the plan over onto my x1, y1 and up through the x1, y1 as it'll appear on paper, just continuing straight on through the x1, y1, and then projecting the heights. All of the heights from the main elevation are the same as in the auxiliary elevation. Heights don't change. Our viewing position changed, but the heights did not. So there we get our edge view of the plane connecting all 3 points, which are collinear. And then we also get the green line right there dropped in, just like that. Okay, so that's the first thing. We have an edge view of a plane. So we have found a view here that shows the plane as an edge view, and that's our first thing. Now, unfortunately, that's not the true angle or the true inclination that the line makes with the plane, of course, as we can probably imagine here. That's probably standing up there at around 75 degrees or so, when in fact the real true angle is definitely not that. You know, it's vastly different. So we can't just, we'll make no assumptions. It's not going to be quite that easy. The next thing we will do though is, once we have our edge view of the plane with this auxiliary found with the edge view of the plane, we're going to project off at 90 degrees to that, and we're going to find the true shape of the plane. So we'll find an auxiliary view showing the plane as a true shape, and then of course we'll bring the line with us. So to do that, we're looking at, I have to extend on that plane here. I'm projecting down from that auxiliary at 90 degrees to it. I'm setting up my x2, y2 at 90 degrees to my projection, and I get my next auxiliary plane. I'm going to need to then project down point P, and then it's point A, B, C, whatever. I'm not sure which ones they are there, but A, B, and C are the 3 points that are on this red edge view, and then point P here, they'll all have to be projected down to the x2, y2. They'll have to be projected along that plane, just like that. And then we'd be, take your distance, so skip a view and work back. And the whole idea of that again, and if you're not sure of that, skip, work back to some of my previous videos there and you'll see it. But skipping the view and working back, so taking the distances from the x1, y1 here back to the plan has to be the same as from the x2, y2 out to the auxiliary plan, because we want the views to marry up. We want them to look the exact same, just like they do right there. Don't be fooled here by the plan or the elevation. It's the 3D we're looking for here. So on the 3D, we'll see the way it lines up so perfectly with the auxiliary plan down there. And my x1, y1 back to plan, and my x2, y2 out to the next plan. Well, the distances have to be the same. So, what else is due to go down there? Oh yeah, the green line. So that's going to have this position right here. Now, that is all I'm going to do at the moment. Okay, I'm going to just set up just that much. And that's just the basic setup of this question. So I'm going to take I'll lay out my coordinates of my points. I'll then find my horizontal cut, which is a strike line. I'll bring it down to plan, which is a true length line on a surface, and I look along a true length line in the surface to get an edge view of the surface, point view of the line. I look perpendicular to that view and I'll get a true shape of the red lamina, and I will get my green line as it sits and as it appears in this true shape view. So I'll get that far, then I'll be back to SolidWorks and we're going to get into the real important part of this. Now here in my worksheet I have laid out points. I've just noted points A, B, C and P right there. So if you're finding it anyway hard to see, A is 36, 14 and 71. B is 65, 95, 10. C is 126, 35 and 29. And point P then at the end of that green line is 116, 72, 57. And the question is, find the true angle that a line makes with a plane. So that's the principle we're kind of covering here now. So I'm going to get started here, and I'm going to lay out first of all the coordinates of my points. So find those points in elevation and in plan, and to do that I'm going to use a starting position of, just from the bottom of my page I'm going to come up 90 millimeters. I'm on an A3 page here for this, so it should fit comfortably. So up 90 millimeters from the bottom of the page, and I'm going to reference my measurements just from the edge of the page right there. So if you're comfortable with it, it's really handy to just lay out all of your X measurements or your in measurements all at the same time, if you're comfortable. If you're not, do them one at a time. So for me, I'm going to go for all of them. So it's 36 for the first one, 65, 116 and 126. Okay. I'm on my up and out measurements, so up from the XY and out from the vertical plane. But before I do that, I might just put them all in, and you might not even see these lines in the video now, but they're all just light projections up and down, and you always measure on the line. That's the key here. So point A was in 36 and it was up 14 and out 71, so out from the vertical plane by 71, and I'm going to label A and A. The second one here was, and I'll just check it, that's 65 is point B, and it's up 95. Let's project that a little bit further. Up 95 is B, and up 95, and it's out 10 from the vertical plane. So there we go, 10 B. The third one that was laid out here was 116, which is point P. Okay, so 116, and you know, even though I laid them all out, I'm going to go back and check. We don't want to make any silly mistakes at the start and get the wrong measurements onto the wrong lines for coordinate geometry. So 116 is up 72. 72 is point P, and it's out 57 for point P. And the final one there of 126 is up 35 is point C, and it is out 29. 29 for point C. So there we go, let's join the dots. A, B and C joining up. Okay, and I'm just going to have a quick look back to SolidWorks here, the model I have done, just to make sure we get this right. The line in question, the line in question that we need to work with is just as it's shown in the question there that I have set up, is from P down to C. So from P to C right there. So that's the line that we want to work with and find the true inclination of. Now I'm going to just go ahead and add a little bit of colour here and there, because I want this to want it to stand out a little bit better. So I'm going to go with the same colour scheme I had in SolidWorks. I'm going to have my green line and my red plane. Now that much is finished, we need to get on to finding our edge view of the plane. So let's get going on that one. We start off here in the elevation with our horizontal section cut, or horizontal or straight line. Right there. That line goes from point C over there to point 1, which is on the line AB. Point 1 on the line AB. And that line in plan is from C to point 1 right there. Again, I'll just keep the colours consistent with what I had there in my SolidWorks model. I think it makes it a little bit easier to understand if we have a nice consistent approach to it. I'll just take away some of my XY line right there, not necessary really. And I'll use my sliding set squares to line up with that true length line there in plan, and I'm going to project along that true length line. I project from B, I project from A, and finally point P right there. I'm going to extend those lines on and project a little bit further. Now, next job is I'm going to put in a perpendicular line for my X1, Y1 line. So I probably should have done that while they were set, but anyway, it'll be okay. I'm going to just line up with one of my projections. And I'm leaving quite a bit of space here now. If I go too close, I kind of just foresee that my second auxiliary might come back on top of my elevation. I'm trying to avoid that if I can, so I'm leaving quite a bit of space here down to the plan. So there is the X1, Y1 line. Now, if we have viewed in the direction along here, and we are viewing along a true length line that lies on a plane, we should end up getting a point view of that line and an edge view of that plane. So let's just see how we get on with that one. We're going to just take, again, if I project from a plan, it is an elevation, and elevation shares, the elevations based on that same plan share the same heights. So the height of point A, the height of point C, and you can label the points as you go if you like, but for this I'm not going to. I'm just going to go ahead and do them all. Point C, point P, which sits outside the plane, and finally point B, which appears at the top here. Point B right there appearing up top. Now what I'll just label C, A, B and P. So I should pretty much get a straight line there for an edge view of A, B and C, which isn't bad. I'm going to drop that in with a red colour because that is the edge view of that red plane right there. Then what do I have? I have P to C is the line that we're working with, and it's kind of the subject of this question. P joined on to C right there, and that is green. So I get an edge view of my plane, and I just have the line appearing as it appears right there. Next I'm going to look at 90 degrees to that edge view. So I'll set up my adjustable for this one. The reason I didn't use an adjustable last time is I think I'd have probably gone way too low down on my board, and the T-square would have been just barely hanging off the edge, so I didn't use it. Now let's project off at 90 degrees to that line. And I'm staying well away from the elevation, so I probably could have kept it a bit closer, but anyway, it works just fine where it is. I won't forget to take point P with me. I'll just extend them on as far as I can here. Now, what are we looking for this time? We're looking for our X1, Y1 line. Sorry, X2, Y2 of course. There's my X2, Y2 line. And I need to take, so if I'm projecting from this elevation, this becomes a plan and my distances. So skip one view and work back to your plan. Now, as you can probably see already, I'm not going to fit all that. That's way too big, it's going to go off my page. So to shorten things up a little bit, I'm going to drop in a reference line that shortens all dimensions. So I might take 100 mil off all of my projections here from plan. It doesn't change the process of what we're doing, it just ensures that it fits on my page. Same principles, just will have to ensure it all fits in. Now for that I'm going to take the angle of my X1, Y1 line, and now angle of my X1, Y1 there, and just bring it on back. Okay, so I'm going to be I'll just bring it to a completely random position, and I might give that a colour as well. Let's put it yellow maybe on that. Okay, so there's my reference line, REF line. So that reference line shortens up all my dimensions for me. I'm going to try and find points A, B, C and P out in my new plan, my auxiliary plan. So this auxiliary plan references from this auxiliary or this original plan. We have point C being the closest to the reference line, out from point C. We have point P being next, out from point P, and if you want you can label as you go. I'm just going to do them all after. Point B is next, and point A is the final one. A bit of labeling there, so it's A, B, don't mix up C and P of course, but there we go, A, B, C and P. A to C. And this view here, if we have looked at 90 degrees to the edge view, we end up getting a true shape of the surface. I always like to draw it in pencil first. I think that it's the only way to ensure that we have accuracy, that we maintain that accuracy throughout all projections and all views. So there it is, drawn in pencil first of all. I'm going to go ahead and just add my bit of shading in here again now. Now, there we go, there's the there's the edge view, or the true shape of the surface. Now I might just drop in a couple of labels there. There's the edge view of ABC, and there is the true shape of ABC. Now we're going to go back to SolidWorks and just see what the next step is. Okay, so what we've done so far is we've found our edge view of the surface and the line appearing in that view. We've found our true shape of the surface and the line appearing in that view. Let's go back and see what we've actually built up here and what the next steps towards our solution are. So back to SolidWorks now. Now back here on SolidWorks, we have exactly what we had on paper. What we're going to do next is this: we're going to construct a cone. Okay, at the moment, in the 4 views that are on the worksheet and the 4 views that we have here, the elevation, the plan, the auxiliary elevation, auxiliary plan, we are not seeing a true representation of where that line is and what, or sorry, we are not seeing a true representation of the true angle that line makes anywhere. Now, you could go ahead doing another auxiliary. One more auxiliary would solve this for us. An auxiliary based on this view, perpendicular to where the line appears. So what I mean by that is, if I was going to project one more auxiliary now, showing from the true shape, showing the, again as an edge view, and I look perpendicular to the line. Now this is there's a lot there in what I'm saying. So looking perpendicular to the line, that's going to be somewhat like this, perpendicular to the line where it appears there. I'll get an edge view of the surface, and that would be up here, and it's, you know, it's almost impossible to see, but that's the edge view of the surface, and that would be the true inclination of the line. So one more auxiliary would work for us based on this line here where it appears on the true shape, looking at 90 degrees to the line. But the second way, and I think the easier way, would be to just insert a cone. Okay, so the cone is going to look like this. We are taking the point P and then the base of the line, and we're just revolving it around. Okay, so we're revolving it around the central axis, being this point here, or in line with this point here. And what that is, it's the path of all lines of a given length and a given inclination to the plane. So I think I'll put it in here in 3D next. And there it is, in 3D. So we are basing it all on what's down here. We have to always on, you know, SolidWorks is great, you can do it instantly in 3D, but we have to base it on paper on a 2D first of all. And that 2D there is the base of the cone that we have here. So I've basically taken a central axis based on this view. So if I look down in that view right there, I've taken everything based on that view, and I've drawn a cone. And that cone represents every line. So that green line was the very first one from P to C. But that green cone represents a rotation of that green line. What that gives us is every line as it lies on the plane. Every line of a given length and a given inclination where they lie on that plane. That will solve it for us. Okay, but how does it solve it for us? What we need to do is project that cone onto our first auxiliary. So just bringing something back from the second auxiliary to the first. Now, if I go at this angle here, we should be able to see the next couple of sketches being added in. I have a 90-degree line right here through the center of the cone. It's 90 degrees to the projections, okay? So I'll project the external points of the cone back, and I'll bring them on up here to my edge view, because of course the cone sits on the surface. And there's the cone right there. That's the cone as it appears in the first auxiliary. If I just turn my view around here so that hopefully we'll see my actual 3D cone line up with its projections here in the 2D view. Just watch this. Okay, we're looking for this cone to line up with them two dashed green lines right there. So whenever that happens, right there, well, I am getting the extreme generator of the cone right now. Okay, if I can see the extreme generator of the cone, I can see the angle it makes with the edge view of the plane. If I can see the angle that the extreme generator makes, I know that all generators on the cone are making the same angle. So that is how we solve this question. Okay, that is how we have to solve it. There's quite a bit to it. There's a fair bit to that now. In 3D, what did we do down here? Well, we dropped in our normal lines and then we projected from each end, and see the way they line up perfectly right here and right here on the ends of the cone. The final little thing I've dropped in there, I'm not sure, it might be asked in a question or it might not. What is find the true angle? Well, there it is. 56 degrees was in this case here on my SolidWorks model was the true angle. Now there's a fair bit of understanding in that. Okay, there's a lot of understanding I think involved in that. But that's it for now. Okay, that's it for the SolidWorks model. We're gonna go ahead now back to the page. We're gonna construct our cone in the second auxiliary view, and we're gonna project it back to the first auxiliary view. Not forgetting that the cone is lying on the plane. It's lying on the lamina ABC, or I suppose we could say it's lying on an extended lamina. You know, if we extended out that surface, every part of that cone is lying on it. Or at the moment, every point on the cone would lie on the plane if the plane was a little bit bigger. So what we do is we project our 90 degrees to the projection lines and bring them back through the views and back up here until we find the cone. It's two extreme generators in our first auxiliary view. So back to paper for a while. Let's see how this solves and works out on paper. Now, as we just saw, we start off up here, we draw our cone. So from point P to point C right there is the generator of the cone. And that, what I've just plotted out, is all generators of the cone. Okay, so I'm going to just, and again, I really don't like doing this, I just don't have a compass at all with me. I'm going to really roughly just dash around the edges of this here. And again, I don't suggest doing this in an exam or any question like that, or even practice for an exam, but when it's just a study sheet that we'll be working from, there's no problem. I'm going to add a little bit of shade around this guy. I'll take some of the shade so that cone's on top of the plane. I'm going to take some of the red shade away from that plane and add in a bit of green shade on my cone instead to make it appear a little bit more 3D than it is right now. Now we're going to bring that cone back here to our first auxiliary view. And what did I say? The first thing I said we'd have to do there, to project it back to the first auxiliary, I need to project the extreme points of it. So that was my projection angle, wasn't it? Yeah, isn't it? That seems to have changed a little bit there now from laying the adjustable down. Really, really important to keep checking the likes of these. I'll just change back my adjustable perfectly in line with my projections. So if I want to draw the cone, I need to know exactly where is the extreme left, extreme right. So the only way to know that is dropping the normal line and then project back from the extreme points onto the edge view. Onto the edge view. And that gives me the extreme generators at both sides of the cone. And what is the cone? Well, the cone is a representation of every possible line, similar to the line PC, similar to that line, every possible line that lies at the same angle that meets that plane right there. And this is the same length, same angle of course as the line, the original PC. And there we go. That gives us our true inclination. I'll add a little bit of colour again. There we go, there's the cone. Now, last thing to take note is that right there, or of course this one here, is the true inclination. And if I just grab the protractor and measure, see if I got something quite similar to the last, to what SolidWorks said. SolidWorks says 56 degrees. And I'm on. I work up. And there's 50, 55, 50, 55 points. It's just, mine's between 55 and 56. So, you know, I think that to be safe enough in saying that the correct answer is 56 degrees right there. And that's it. That's the true inclination of a line to a given lamina, and that was all constructed using our coordinates of our 4 points right here. So not the easiest question of all to get here. I might just, you know, I might take a minute now and just update my SolidWorks model and go through it using the second method. Okay, but that's it solved. In a sense there, that's the whole question solved using our cone method right there. Now, as I said in some previous videos, if I haven't confused you yet, wait for this one. So, we have solved the question. We have found that the correct and true inclination that green line makes to the plane is 56 degrees. And we solved it using the principle that all generators on a cone based on this plane are going to be at the angle of 56 degrees. So if we can see any one of the extreme generators as we just did at 56, well, we know that that line there has to be 56, the original. The second method that I briefly touched on a while ago, and it really wasn't awfully apparent to me until I was looking through my SolidWorks here, without the cone. Okay, so if I go ahead and just hid that, let's say, and if I hid this line here, and maybe if that has selected my projections back, if I hid those without that cone, and maybe I'll be able to hide it here as well in the 3D, which might just bring a bit more understanding to what we're doing here. Without that cone, we can still solve the question, okay? And the question can be solved by viewing at a projection from this view, from the true shape view, at 90 degrees to the line as it appears. And what that will give us is this. Okay, there's the line as it appears. And if I get a view, and of course, all of these views and viewing directions just give us a good direction to see the 3D. That's what we're actually doing on paper. We're using all of our 2Ds to view a 3D that we can't see on paper. We can only see 2D representations of it. So when I turn and I view, again, if I have a true shape here, and if I look 90 degrees, if I look any angle at all, based on that true shape, I'll get an edge view in my next view. So if I keep turning until I'm looking 90 degrees to this line here, I should be able to see a true inclination of the line to the plane, you know. So look, let's see how it works. Okay, we might as well see it in action rather than talking too much about it. and we'll see if we end up with the exact same 56. I think this one was actually 56.2 or something like that. Let's see how we go. First thing is I need to extend down my plane right here, and then I project off at an angle. I started there at point P, I think, so projected at 90 degrees to the line. Okay, projected off, stopped at that position, any position at all, and that'll give us our next plane. So now this right here is kind of a bit crazy, I suppose, in a way on paper, but we won't overcomplicate. We have an elevation plan, we have an extra elevation, we have an extra plan, we have an extra elevation. Auxiliaries all link up, but basically all planes and auxiliaries are all based on this original right here. So the distances will be easy on paper, they'll be very easy, okay, but what I did was I took points A, B, C and P, projected them up onto my auxiliary view, and then I'm projecting them back actually to here. So what we're doing, think about this for a second. I want my distances this view, I'm going to skip this view here, go to the previous XY and work back. And why does that work? Well, there we are. Everything from my 3D projects up, touching my first auxiliary perfectly. I've skipped this view and I'll be taking my distances back. So we'll see how that works in just a while. What do I get up there? I get an edge view of the plane, and I get the green line appearing just like that. Okay, so it's just another view that shows an edge view of the plane, and it shows the line appearing to touch, and there it is. Okay, edge view and line appearing like that. And if I just go ahead, I'm going to have to just sketch over these right now. If I sketch over them lines for a second and drop in 2 lines like that, and just smart dimension and see what my angle is, I'm getting 56.24 degrees. So the exact same as I had in my previous, using my previous method, 56.24 I think it was. So it's just a second way to solve. Okay, where it's a second route to getting the exact same solution. So once we get to this true shape, it's either a cone or another auxiliary view. I'm going to do that on paper. It won't take probably longer than 1 minute to do on paper. And please don't get confused with this. It's just another route to the solution, and that's all. So back to paper now for a while. And here we are. So let's get this done nice and quickly. We won't worry too much about this. I'm going to set up the angle that line from P to C is here in my auxiliary view. That is point P and that is point C. So I'm going to set up the angle of the line P to C. Now, I have a feeling that it's going to be harder on paper maybe to keep the accuracy. Degrees could go off by a little bit here because it's quite a short line to be basing a whole auxiliary view on. But we'll go as accurate as we can. P to C. That's quite good there. Oh, where do I have space? No, I have space anywhere I want really. I can view to the right or to the left. For now, I'm going to view over here towards the left side. Point C. Point P. Point A. And if I just rub off that projection a little, make that a bit shorter, I need to just take point B finally. Now, I need my, what's this? X1, Y1, X2, Y2, X3, Y3. I need my X3, Y3 line. Now, the simplicity of this is very, very handy here if we don't overcomplicate it in our own heads. And what I mean by that is we're going to use the same principle for this and the same little bit of thinking and theory, that the distances here come from skipping one view and working back. Okay, so for this view you skip the previous and work from the XY line back, and that's it. That's all it's going to be. Now we're going to have to shorten it up because again I don't have that kind of space left on my page, so I'm going to shorten this up a little bit. I'll take the X2 Y2 line and I'll bring it back, and I'll bring it right back pretty. I'm going to bring it pretty close now. I could easily put it on the red line, but I'm not going to. I'm trying not to confuse too much. So I'm going to just stay off that red line a little bit. I'll use that brown line there as my REF. So that's a reference XY line. And time to get the compass. So the distance is for A, B. So A projected out, C projected out, and B. So skip this view and work from the XY line back, or in this case we'll shorten everything by about 90 mil or 80 mil there, and we'll work from my reference line back. So A, B and C will all fall in line because that's the distance back to B, back to C and back to A. So they'll all fall in line. From there to there. Just to ensure that's accurate, I'm gonna, if they're equal distance there, if they're equidistant from the XY line up there, I should be able to do it with my adjustable. And I'm going to go ahead and just put that in there red as well. That is once again an edge view of the plane. What else do I need? I need the point P. From the reference line now, of course, not from the red line. From the reference line back to point P in this view can be projected up from point P. Sorry, I just made my mistake right there. It's the orange and red, probably not a good choice of colour. The distance back from the reference line up to P, from P on the XY line, of course, up to P. There's point P, there's point C, there's point A and B. So the line in question here is the line joining the points C and P, and in particular it's just this portion that's important, but I extended on there on purpose. I wanted that, I should have drawn that green I suppose, but oh, little slip there. Okay, I'll leave it there. Nothing we can do about that now. That's the beauty of fine liners. So what have we got? We have a view that appears to show P to C based on that edge view. Let's see if it's correct. Let's see how good or bad this is. And the angle I'm seeing here, if I just carefully line it up with the baseline, the red, is up to 50, 55, 50, yeah, it's 55 or 56 degrees I'm showing there. So, you know, little inaccuracies aside there, that's a pretty good indication that the method is perfect, isn't it? So there we have our 56 degree true inclination shown once more, no cone needed. So that's just the second method, and as I said, I just love confusing people. Well, I think it's easy to get confused at times, but at the same time, if we can understand why we viewed in that direction, finding this view is not going to be a big problem. So there we go, that's that question solved in two different ways, but really we've had to go 90% of the journey for either method by finding our strike line, finding our edge view and line, finding our true shape and the line PC, and from there you can either use your cone method brought back to the first auxiliary, or you can use a third auxiliary view to show the one true view where that line appears as a true angle to the plane. So that's it for this question. Let's get on to our next one. Now I'll freeze this video, I'll pop the next SolidWorks model up on screen, and we'll get cracking on that. Now on this next and possibly the final question for this topic of plane and descriptive geometry, I have the 3 points ABC on a lamina mapped out, and again I will give the coordinates to these points when we get back onto paper. And I also have a point P right here, and the coordinates of that point will also be given. If we just have a look at what we have here, point P is floating in space, it's not on a plane here of course. And the question that we will be solving here is, we want to find the projections of a line from point P. The line has to be three things. It has to be 38 millimeters long. And of course that can change, that could be anything. That's not really the purpose of the question as such, but it has to be 38 millimeters long in this question. It has to be parallel to the vertical plane, so it must be lying parallel to the vertical plane, but it also must lie parallel to the lamina as given. So there's just, you know, a little bit of learning, a few extra principles involved in this one here that we'll go through. First thing I have here on SolidWorks is I have the elevation of the plane of the lamina and of the point, and I have the plan of the lamina and the point. Now I'm going to leave them there for a few minutes, and then I'm going to hide them again because I think I don't want to overcomplicate what's coming up. What do we have next? Sorry, now I should just 1 second. We are looking at starting solving this question, so we can't solve it all in one go. Okay, it has to be 38 millimeters long. It has to be parallel to the vertical, and it has to be parallel to this lamina. We can't solve everything at the same time, so we maybe relax the question a little bit. We'll go back and solve two parts. We're going to draw all possible lines that are 38 mil long that are parallel to the vertical plane. And what we get by doing that is we get this, basically it's a disc, it's a flat disc, it's not a sphere or anything, it's a flat disc. And if I sketch any line that is on that surface, any line from that point P out is 38 mil long, and any line that I drop here is also parallel to the vertical plane. So that disc gets us started. It satisfies two of the constraints. There are three. The third constraint is that we need the line that we pick, which will be from the point P out to the circumference someplace. That line that we choose has to be parallel to the plane here. So it's probably going to be a line going down in this direction here. Okay, now that's the start. That's the beginning. I'll just accept that sketch that I had started there just as we were talking about it. That's how we get going, is it? We kind of satisfy two things to begin, and then we go ahead and we'll try and figure out the third one. We'll get an edge view of the plane, because an edge view will show us the plane. It'll show the true inclination it makes to the ground there, but we'll also maybe be able to work out something parallel. If we get an edge view, we can go parallel. And we'll project from our horizontal section in the elevation projected down to plan, seen as a true length and plan, and then of course the usual, there's our true length line on the surface, and we'll look along that and we'll find the point view of the line, edge view of the surface, the usual. We'll do some projecting, so now ignore that, and we will, sorry, now it's just when I'm staging these in, they don't seem to work as well sometimes. So I've projected along in line with my true length line on the surface, and I'll project and find my all projections, including the point P, of course, which is just right there. That's the center point or that's the center of the disc really. But we project everything across, and we get an edge view of the surface. And what we also get, and this is the important one, when we look at this disc here at an angle, well, anytime you project a circle at an angle, it'll appear as an ellipse. Okay, so we'll get an elliptical view of the disc. Now, does it matter that it's an ellipse? No, it solves the exact same problem for us. It gives us, again, the path of all possible lines. So if I just start to sketch right here, from the center up to there is a line 38 mil long that's parallel to the vertical plane. Same thing here. That's a line 38 mil long parallel to the vertical plane. It's just appearing shorter. Now, what about the one that's parallel to this plane as well? Will we then have satisfied all of our constraints? So what we're looking for is this, except that sketch, what we're looking for is this line right here. That red line right there is the one line that appears to solve all three parts of the problem. Number one, it's 38 mil long because it's on the radius. Number two, it's parallel to the vertical plane because it's on the disc as well. And number three, it's parallel to the lamina because it appears parallel in this view right here. If a line is parallel to a lamina in any edge view, well, it's said to be parallel to the lamina. So if we see an edge view of lamina and the line appears parallel, then we are assuming that that is parallel to the lamina. We know that. I'm projecting the end point of the line back onto the disc here in the elevation. Okay, and then finally we draw the line, and that's it. That's the question solved. So in theory it appears quite simple, but maybe it's not quite that simple. You know, it's not bad, but let's just get going. That's the theory behind it. That's the principles there, and let's get back to paper. So the coordinates are set out here in the top corner, and again, just like last time, if you find it hard to see them, listen up and write them down. Point A is 51, 65, 77. Point B is 165, 96, 15. Point C there is 109, 8, 109. And point P is 55, 96 and 25. The question: find the 38mm line from point P that is parallel to the lamina ABC and parallel to the vertical plane. So that is our question right there. Let's get started by going up from the bottom of the page. I'm going to measure up 120 mil. 120, and I'm going to draw my XY line right there. And from the left hand point right there, I'm going to go ahead and just map out all of the points exactly as they're given. So just like the last question, I'm going to go ahead and just do them all at the same time. 51, 55, very, very close, so I'll be careful thereafter. 109 and 165. I'm going to project up and down. So point A is the 51, which is the first one, up 65, out 77. So up 65 to A and out 77 to A. What was the next one? So that's the 55 mil, then is point P. So up 96 and out 25. The third one is 109, up 8, and that is point C, and it's out 109. And finally, the 165 is up 96, and that is point B, up 96, and it's out 15. B. So ABC joined. Just like last time, I think I have this one coloured as a red plane again. Or a red lamina, I should say. A, C is there. And finally, same in plan. Now a little bit of shade added to that. And there we go. So let's get going on this one. So from point P, we want to draw a line 38 millimeters long, parallel to the vertical plane. So let's do that one first of all. Let's start off with just one line. One line from point P, 38 millimeters long, parallel to the vertical plane. There it is. That's just one single line. Then let's go for all lines that are 38 mm long from point P parallel to the vertical. And that is all possible lines. And this is not a cone, by the way. This is a disc. Okay? It's a flat, planar circle. So it's a disc. that is every possible line 38mm long that's parallel to the vertical plane. Let's draw that in plan. As it appears in plan, it is from extreme left to extreme right, of course. It is here to here. Now, viewing the XY there, and where is it in plan? It is here. There is the disc as it appears in plan, from extreme right to extreme left. I'm going to add a little bit of shade to that. And there we go, that disc right there represents two parts of my question solved. So if I just tick them off, find the 38mm line, okay, I've that done, from point P that's parallel to the lamina, no, parallel to the vertical plane I have. So I have right now found every line that's parallel to the vertical plane that is 38mm long. So the big one I'm left with is parallel to the lamina ABC. So let's go ahead and find an edge view of the lamina. If we can find an edge view of the lamina, we can set the line parallel to that edge view. So let's take our horizontal cut. From point A to point 1, which is on the line BC. Let's drop point 1 down to plan, down to the line BC. Point 1. Which gives us a true length line on a plane. Right there. There's a true length line, and we're going to view up along that true length line. So that gives me a viewing direction. Go ahead and set my adjustable in line with that blue true length line. And project. Just rub out the excess of the original XY that I don't need. Take point B, and I'll also just take, for now, just point P here in the center of the disc. And there we go. I'm going to draw my X1, Y1 line. And I'll just take a few points. I know I have a lot more work to do, but I'll just get going. We'll get building up. Let's start getting ourselves a few marks here by taking some of the points and setting them in this auxiliary view. So right now we have an edge view of the surface, hopefully. We've looked along a true length line in the surface, so we should have an edge view of it. So there's point B. And there's the 3 points for the edge view of the surface. While I'm here, I'll also go ahead and take point P, the center of the disc, and the extra point that was mapped out on this question. So we get edge view of the surface right there, which can then be just dropped in as a red line. So edge view of the surface given, and that is point C, that is point A, and that is point B, and this right here is point P. Next, I want to find my disc up there. So to find that, we're really back to what we have done back in probably early second year when we started working on auxiliary views. An auxiliary view of the circle, well, all of the projected widths are going to come from plan. We'll use the same blue viewing direction, viewing up from the plan, and the heights of this elevation come from this elevation. So starting with point 1 here on the left, and for accuracy then breaking it up into our 12 sections. Projecting all of those down into the plan. Projecting them all up onto my auxiliary view. Next, taking the heights from my main elevation, setting them to my auxiliary elevation. Now what I'm going to do here is this. I'm just going to take 10, 11, 12, 1, 2, 3, 4. I know that 3 and 5, 2 and 6, 1 and 7, they're all the same heights. Basically, they're all the same distance up from the XY line. And that means that they're the same distance up from this XY line. So I'm just going to project the heights for 1/2 only, and that means I'll have 1/2 of the curve done, and I'll mirror the heights down parallel to the XY line to the other half of the curve. And there we go, there's the disc shown exactly as it is in the elevation heights all taken across. I think I might have maybe taken a slightly incorrect or inaccurate height there for point P on my originals. That's why you'd see me just checking it a couple of times, but all fixed up, mirrored across then from 11 to 9, 12 to 8, 1 to 7 and so on. Mirrored through the central axis, or we could say just heights projected across parallel to the ground, exactly as they are from 2 across to 6 being the same height, and from 2 projected parallel to the ground to 6 to establish the same height. Now, final stage here is this. We're going to go ahead and say that, first of all, any line you draw from point P onto the circumference of this disc is going to satisfy the 38mm and parallel to the vertical. But the only one that will also satisfy, well, there's just 2, I suppose, really, but the one that I'm going to draw that satisfies this part, all 3 constraints, is right here. From point P, drawn down, I'm going to go down. We could also go up, of course, because that still solves the question. But from point P, working down to hit the outside of the curve, parallel to the edge view of the surface. That's the one we want. As I said, we could also go up there, up towards point 1 to 2, but I'm going down and I'm near 7 to 8. So that's the one I want right now. I'm going to take that back down to plan. Okay, and it is here. I'm going to project that up to the elevation. Now, that's a hard one to get it accurate. Okay, so is it perfectly accurate where it goes down? It's so close, it's dependent on my freehand curve as well, of course. I project it up to the elevation, so it should be there. And just to ensure that I'm accurate here, and just as one quick check, which only takes a few seconds, the height up to the end of that red line right there, should it, and does it match? Yeah, that's pretty close now. It matches up with the height to the circle in the elevation. So there we go. That is the line in the elevation that solves the question. And I should show it in plan. Right there. So that red line shown in the elevation and plan, and of course over here, solves the third. Okay, it's parallel to the lamina ABC, it's parallel to the vertical plane, and it's 38mm long. Now, this second half of the video wasn't too bad. The first one, there was a little bit more thinking involved in it, but that is it. That's the principles involved in that question and the method of solving it. So I hope this video helps, and I hope you have found all these videos on plane and descriptive geometry to be clear and concise and helpful. So if there's any extras you'd like to see, leave me a comment here below the video, and thanks very much for watching.